Hi, I am Farhan Fadabir. As the third assignment of the Spring 2023 Machine Learning course, I am presenting the paper titled Dueling Network Architectures for Deep Reinforcement Learning. It was published in ICML in 2016 by a group of researchers from Google DeepMind. This work has nearly 3.5 thousand citations as of today. Let's take a look back at the basics of RL. On the left, you can see a basic reinforcement learning problem. Reinforcement learning involves an agent and an environment. The agent takes an action in a given state of the environment and receives a reward based on the interaction. The objective is to train the agent to receive the maximum cumulative reward. The Q value denotes an agent's expected cumulative reward from a given state and action pair. The conventional deep Q network, or in short DQN, takes states as input and outputs the Q values of each action. This is shown in the left figure. Here, the network can be a conventional neural network or any of its variants. For environments involving pixeled image input like the Atari games, the DQN network involves convolutional layers. On the right, you can see the proposed network in the DQN paper. In this implementation, there are 3 convolutional layers along with 2 fully connected layers. Now let's take a look at the problems with the vanilla or conventional DQN shown in the previous slide. This is an instance of an Atari game named Sequest. The goal is to retrieve maximum divers while dodging and blasting enemy subs and killer sharks. Points will be awarded accordingly. Moreover, the oxygen tank needs to be replenished at a certain interval. The upper right bar chart shows Q values for 18 actions and marks the best action in red. For this instance, the agent will choose the compound action downright fire. However, the subtle problem with this DQN architecture can be identified from the bottom right graph. Here, it shows that the differences between the maximum and minimum Q values are very small, which results in slow learning. To circumvent this issue, the dueling architecture decouples the state value from the actions. Here is the contribution of the work. The proposed architectural improvement is shown on the right. Here, as you can see, the DQN and dueling DQN networks have the same structure up until the feature extraction layer. Afterward, the features are split into 2 separate streams representing the value and advantage functions. The value stream has a single output neuron, whereas the advantage stream has the same number of neurons as the actions. The advantage values denote the advantage of choosing a particular action over the others. Both of these streams are aggregated at the output layer, resulting in Q value similar to the vanilla DQN architecture. The proposed network does not show any explicit benefit in the forward pass over the conventional DQN, as both estimates the Q function. However, the benefits occur in the training phase. During backpropagation, only one action can be evaluated. It denotes that only one output neuron contributes to the training process per training sample. As a result, the training of the neural network becomes sparse and biased for environments with a high number of actions. This particularly occurs in the conventional DQN architecture. Separating the state value function enables the learning of the state value functions efficiently in each training step. On the other hand, the advantage value shows a normalization effect which will be more apparent in the aggregation method, which will be discussed in the coming slides. Now let's take a look at the aggregation of the value and advantage streams. At first, the advantage values are subtracted by the mean advantage values, which result in a zero mean normalization. Then the state value and the normalized advantage are simply added to estimate the desired Q values. The effects of the dueling architecture are shown here. The upper left graph shows the separate state value and the advantage values. As you can see, the advantage values are normalized around the zero value. This also results in better Q value separation shown at the bottom left. Here you can see the dueling DQN demonstration for the Atari game Enduro using saliency maps. In the first instance, at the upper right, the value function pays attention to the scores and the road near the horizon to look for incoming cars. On the other hand, as there is no car on the horizon, there is no action to be taken. So the advantage function does not pay attention to any particular pixel region. In another instance, at the bottom right, the value function again pays attention to the scores and the horizon, but this time it also looks into the oncoming car as it might affect the overall value. The advantage function, on the other hand, pays attention to the oncoming car as a new action must be taken to avoid collision. In terms of input and output, the dueling architecture is the same as its predecessors. As a result, it can be used with other proposed algorithms like vanilla or conventional DQN, double DQN, prioritized experience replay, or in short PER. The dueling implementation adopted the same preprocessing scheme, epsilon greedy policy for exploration, as the vanilla DQN. Also, it implemented the prioritized experience replay and took 30 no-ops action to ensure a random start for Atari games. Here is the performance of the dueling DQN compared to the conventional DQN in a simple corridor environment. As you can see, with the increase in the number of actions, dueling networks start to converge much faster than the conventional DQN networks. Now let's take a look at the normalized performance of the dueling DQN compared to the double DQN. As you can see on the right, dueling DQN outperforms double DQN for most Atari games. The table shows dueling DQN with prioritized experience replay and gradient clipping, showing a significant improvement in performance over its predecessors. Although the dueling architecture shows a good improvement in performance for most of the games, it shows no improvement with games having sparse rewards like Montezuma's Revenge. Such games need longer exploration, which is not improved with the dueling architecture. Also, it does not show significant improvement in environments with fewer actions. Overall, this work proposed the first big improvement in the deep RL architecture. The dueling architecture decouples the state values and actions, which resulted in efficient learning for a wide range of environments. This architecture was also compatible with other proposed algorithmic improvements like double DQN, prioritized experience replay, and so on. It shows a significant performance boost in 36 out of 57 Atari games. Here are the references of this presentation. Thanks a lot for listening. Have a good day.